This is 8.3, second part, geometric sequences and partial sums. In today's lesson, you will find the nth partial sums of geometric sequences and find the sums of infinite geometric sequences or series. Here is one of the formulas. This is for the sum of a finite geometric sequence. And notice that there is an end to this. That's what makes it finite. Okay, the end means that there's a place where you're going to stop. And this is the first term. This is a common ratio. We learned about that yesterday. The common ratio is how much each term is multiplied by to get the next term. And my index starts at 1. And the exponent on here is the index minus 1. So the first one's going to be 0. The exponent's going to be 0 when I is 1. The formula you're actually going to be using is going to be much easier. This is a simplified version of this, and we get this from, you remember Gauss's formula, okay? And this is the first term times 1 minus the common ratio to the nth power all over 1 minus the common ratio. Okay, let's see how this is used. Find the sum, and notice that this is a finite sum because we have a number up here. We have an ending limit. If this was an infinity symbol, this would be an infinite sum. Even though it has an infinity symbol up here, we could be asked to find a partial sum, like the third partial sum, which would be the first 3 terms added together. But right now we're going to stick with the finite. We have 12, so we're going to have 12 numbers that we're going to add together, and the first one begins with 1. So looking at this, we have to be real careful. We just can't grab this as the first term. We actually have to plug in the first number down here to get our first term. And we plug in 1, substitute the 1 in for n, we actually get this, which is really 1.2. And 1.2 doesn't mean show up in here. That's really important that you can find all your pieces. You need to be able to find the common ratio. That's 0.3. That's whatever is the base of the exponent. Okay, the base of the exponent is your common ratio r. And then to find the first term, you actually have to plug in 1 for n in order to discover what that is. Okay, that's kind of important. R is my base of the exponent, which is 0.3, and n is 12. So we're going to have 12 pieces that we're going to add together. But we don't need to actually do any adding because we're going to use this formula. We're going to take A1, which is 4, times 0.3, and then we have 1 minus the common ratio to the 12th power to the nth power, all over 1 minus 0.3, the common ratio. That's going to give me the sum of 12 terms. Okay, finishing this off on my calculator, I get 1.714, rounding just to 3 decimal places. Alright, let's try this again. Remember that you're going to be using this formula, and you're going to be picking off the pieces off of here. So, given that this expression, we're going to find the sum. So this geometric sequence, we're going to find the sum. First, we're going to find the first term, because we need the first term to use this formula. So we're going to put in 1 for n. And 1 minus 1 is 0, 2 to the 0, or anything to the 0 power is 1. So you notice that the 1 was actually the coefficient in front of my 2, and the 2 is my common ratio. It's the base of my exponent. Whatever is the base of the exponent is always going to be my common ratio. The first term is the one that's a little tricky to find. So if it goes from 1 to 7, we have 7 numbers, so we have n is 7. Then putting this all together, we have the first term 1 minus the common ratio of 2 to the 7th power all over 1 minus 2 to the 7th power is, I believe, 128, and then we're finishing this up, we get 127. Okay, this does not need to be rounded. Alright, moving on. I want to talk about my infinite sums for the geometric series, and I'm going to talk about the growth and decay. It's really important because you have to find out when it's even possible to find the sum. If r, the common ratio, the absolute value of it, just take off the negative sign, if the absolute value of that number is more than 1, it's going to keep getting bigger. It's like if the first one was 2, and the next one's 4, and the next one's 8, the next one's 16, 32. If it asks you to find the infinite sum, you're going to say, well, that can't be possible because I can't ever find the infinity because it's going to keep getting bigger and bigger and bigger. There's no way to capture that. But if the common ratio, the absolute value of the common ratio is less than 1, then it's going to be like a decay where this would be 10, and the next one would be 8, and the next one would be 6, and so on. It's going to get smaller. We can actually get a sum because eventually, but we're going to get to a number that's so small that we can actually add them together. Okay, where if it's growing, if the numbers are growing, we're not going to be able to add them, so there's no infinite sum. But if the numbers shrink, then we can get an infinite sum. Some examples for r would be 2, 19, negative 1.1, because we take the absolute value of these numbers. And as long as the absolute value of these numbers is greater than 1, like negative 20, even though negative 20 is smaller than 1, but we take the absolute value, it's going to be greater than 1. Numbers that will work, these don't work. The numbers that will work would be anything that has a 0 point something, even though it's negative. 0.2, 0.019, negative 0.1, and negative 0.99. All those work as long as they're going down. You notice we didn't put the case where r is equal to 1. Well, r is equal to 1 will not grow. It'll just remain the same all the time. That's not a geometric series at all because it's not growing. Multiplying by 1 doesn't change the number. I'm going to tell you that these are the same because sometimes your book will write it this way and sometimes your book will write it this way. They flip back and forth, so you need to know that they're the same. Now, we normally start our index at 1, so this is the one that you're most familiar with. So you're going to always take 1 away from your index in the formula for an infinite sum. Now, if you happen to start at 0, then it's going to be just your index. It's not going to be minus 1. So just know that if you start at 1, you have to subtract 1 to make this 0 power, to make r to the 0 power 1, so that this becomes your first term. But if it starts at 0, then you don't subtract the 1 because r to the 0 is 1, and that will give you your first term. Alright. For I is equal to 1, then 1 minus 1 is 0, r to the 0 is 1. And when I is 0, r to the 0 is 1. Okay? If this is 1, that's how you're going to know that this part here is your first term. So here's your formula. And remember that if r is greater than 1, then there can't be a sum, an infinite sum. But if r is less than 1 and n is infinity, if this goes to infinity up here, then you can have a sum. This is my finite formula up here, not my infinite formula. What happens if we let n go to infinity? What happens if we let n get really, really huge? Like this n over here, we get, let's call it 1,000. If we have a number that's less than 1, let's say 1/2, to 1,000 power, the 1/2 to 1,000 power is going to make this really small. This is going to go so small that this is going to disappear. and then my formula for finite becomes my infinite formula, and that's 0. Okay, so that means that my infinite formula, this part right here, will just become 0, and we'll just have 1 over 1 minus r. So 1 over 1 minus r is going to give me my infinite sum. You notice that infinite sum is much simpler. There's no n involved because the n doesn't show up here. If there's an n up here, then you have to put an n up here. Okay? And it's going to get so big that's going to make this go to 0. So we're going to have 1 minus 0, and we don't write that. Okay, so there's your two formulas. They look awfully similar. Okay, this is the finite sum. This is the infinite sum. Finite, n up here. Infinite, infinity up here. N up here, no n here. All right. We're going to use our calculator to find the first 6 partial sums and then find the sum. So the first one is putting 1 in for n. I get 0.6 to the 0 power, which is 1. 1 times 4 is 4. R is 0.6. And since R is less than 1, we're okay. Always check this because they're going to give you like 5 in here, and you're going to do all this work, and you're going to find, oh, there was no sum. And now we don't have to check anything else, right? We have A1 and R. We're ready to put it in our formula. So now A1 times 1 over 1 minus R, and then this is 4 times 1 over 1 minus 0.6 is 0.4, and that will equal 10. Okay, if you if you can do the math here, just that's 10. Or if you insist, you can put this in your calculator. You should know that 0.4 goes into 4 10 times. Okay. All right. Let's try another one. Use your calculator, find the first 5 sums, and then find the sum. So we're not going to actually find the first 5 sums. We're just going to find the infinite sum. Okay, so notice that we're starting at 0 here. And this is how we what happens when we use our calculator. We get that. And so the first one is going to be 5, because 5 times 1/2 to the 0 power, anything to the 0 power is 1, that's 5. And R is 1/2. And since R is less than 1, we're okay. So we're going to go ahead and finish. So 5 times 1 over 1 minus 1/2. 1 minus 1/2 is 1/2. So 1 divided by 1/2. 1/2 goes into 1 2 times, and 2 times 5 is 10. Now don't get tricked into thinking that since the last problem is 10, this problem is 10, it's always going to be 10. It's hardly ever going to be 10. It's just that these two problems came out to 10, even though they were completely different. I wanted to talk about this for a second. This is the first 5 partial sums. This is not the fifth partial sum. Okay, the fifth partial sum would be this number right here. This is the first 5 cumulative partial sums. That means this is the first term. This is the first term plus the second term. This is the first term plus the second term plus the third term. Each one of these is added up of all the terms before it. So this is the first one. This is the first one plus the second one. This is the first one plus the second one plus the third one. And this is the first one plus the second one plus the third one plus the fourth one. And this is actually the fifth partial sum right here. This is the first one plus the second one plus the third one plus the fourth one plus the fifth one. The reason why they asked you to do this, they wanted you to see that these are growing, but they're growing slower and slower until they start approaching this number, 10, infinity. Okay, these are all getting closer and closer to this number. Right. Okay, this is your Google form. This is your first Google form. What is the first term of the summation notation? These are your choices. Number 2, what is the common ratio R for the summation notation? What is the first term for the summation notation? There are going to be 8 questions altogether. What is the first term of the summation notation? What is the common ratio R for the summation notation? What is the first term of the summation notation? Find the finite sum. Notice the 6 up here. We're going to have a finite sum. Okay, find the infinite sum if it exists. And that's the last one. Okay, that's it.